I'll also share my screen. All right. So, according like we discussed in the last class, some of these procedures on how you can manage data and things like that. And so today we will start some of these examples in scientific computing. So one of the very fundamental examples is like how to do numerical integration, and this is one of the most well-known examples. Like if you have to do multi-dimensional integrations, you can use some sort of parallel programming. There are caveats to it, but again we will come to that, and we will go into some matrix vector or matrix multiplication type operations, and we will see how we can do a bit of how to solve linear equations using some iterative techniques. So we will start with the numerical integration procedure. So before I go into that, I'll just talk about a little bit of the how you do it. So if you have a 1D integral, how you generally do it is you use something called the trapezoidal rule. So in the trapezoidal rule, that is one of the procedures. There is some other procedures as well. Trapezoidal rule is popular. So what you do in that is, let's say you are going to integrate from 0 to 1. All right. So, but let's say 0 to 10 or something, or 0 to 1. So what you do is you divide the region from 0 to 1 into small boxes of equal length, and let's say the size of the box is h. So let's say if h is 0.01, you will go from 0 to 0.01, 0.01 to 0.02, so on and so forth, and until 10. And then you will have the function. Let's say you're doing a 1D integration, one dimensional. So that is nothing but the area under the curve of that function from between 0 to 1, correct? So then what you will do is, then you will start drawing small trapezoids such that the trapezoid is contained between the x-axis and your function fx. And how is it become a trapezoid? If you take a small enough h, you can approximate the function by a straight line from x to x plus h of some slope, and therefore you have a trapezoid which is bounded by x, x plus h, the x-axis, and the function between those 2 points. So that will look like a trapezoid. And then what you can do is, then you can just sum up all the areas. You know the formula of the sum of area of a trapezoid, that is like half sum of parallel sides into height. And then what you can do is you can just sum up all the areas and you will more or less get the value of the integral. And this is a very standard procedure. Now if you think about this problem, this whole business of dividing of the whole in range from 0 to 1 into small pieces and then adding up their sums, this is inherently a parallel process, correct? So I mean, you can divide the whole domain into 2 parts and then make the sums parallelly, and so on and so forth. So this is one of the very parallel routines which you can write. Now as we had discussed the day before, since if you are now going, this is a 1D integral, correct? So if you are going to divide one of the axes, now you are only integrating along the x-axis, let's say, and you can divide it into n parts. And higher the value of n, more or less better your accuracy will be. You cannot increase this indefinitely because then the question of machine precision and things like that come in. But apart from that, higher the value of n, more or less your result will be better. But let's say now you have a multi-dimensional integral. You have a 2D integral where you have to integrate over x and y. So you might have seen integrals like e to the power x square plus y square dx dy, things like that. So you are integrating and finding the area of a surface. So in that case, there are many ways to do these type of problems. One way would be to just do a straightforward generalization of what we just discussed for a 1D integral to a 2D integral. For example, then if let's say you are going to integrate between 0 to 1 along x and 0 to 1 along y, and if you take 10 divisions along x and 10 divisions along y, and then you can apply the numerical integration rule, and you can find out the area under the curve. and basically you are going to evaluate the function value at those points at some x comma y, and take the area as a sum of over that whole region. So again, this procedure can also be done parallelly, because you can uh, take the sum of one area in parallel with the sum of another area, and so on and so forth. Therefore, this procedure is again parallel. So now the issue here is what happens if you are going to take n to be quite large. That will scale the number of points where you have to evaluate the function will scale with the dimension. So if you have taken a one-dimensional integral, you will only have to evaluate the function at 10 points. Now, if you have taken a two-dimensional integral with n division or 10, let's say 10 divisions on each axis, you have to evaluate the function at 100 points. You can imagine it will keep increasing with the dimension. So it will scale as n to the power d, n to the power d, where d is the dimensionality of the integration you are trying to perform. So this is one of the issues, like that if you have to do a 2D integral 100, 3D integral it will become 1000, so on and so forth. So what will happen is the procedure remains parallel but becomes very compute intensive, and you can therefore parallelize and use GPUs for it. Now, I should mention one point here. Since this is just an example of parallelization we are doing, but so we are discussing this example. So I think mainly in practice, higher dimensional integrals are generally done using something like a Monte Carlo or a stochastic method, where you sample the points randomly depending on the function you have. But as a instructive example, a multi-dimensional integral is a cool example. So maybe we will look into this problem now. Okay. So the function we are trying to integrate here is given by this. This problem, if you look at it, the function we are trying to integrate is f. So what we are doing here is, where this function is coming from, let me just give you an idea. This we will see in the next class when we solve PDEs. While solving PDEs, you need to solve for the coefficients. Like if somebody knows about what is called the separation of variables method, you have to find out the coefficients involved in the series expansion. So in that scenario, you have to use the initial conditions and you have to perform an integration. And that will, if you are going to, let's say, solve a wave equation or a heat equation in 2 dimensions, it will involve a 2D integral, which will look something like this. This sign, this and this part comes from the mathematics of the PDE, and this initial part of the function comes from your initial condition. So to find out the coefficients, you have to perform this integration. In certain cases, this integration can be performed analytically, but if your initial condition is difficult, as in complicated analytically, and that in those scenarios, you might not be able to perform this integration. So let's say this sort of a, but then that is the context of this integration. So we will now just deal with this integration. So what we have taken is, we are going to integrate this function into dx into dy, and from 0 to 10 on both axes. See, I have defined a constant c, which is varying from 0, which is 10, and therefore we will integrate from 0 to 10. And we'll integrate this function dx dy, and we'll integrate from 0 to 10. So I guess this is, as I said, this is a very easily parallelizable problem. You just have to discretize your grid. So now you have a 2-dimensional grid, right? So you just have to discretize the grid, and you will have 2 indexes, I and j. These indexes will run from 0 to n, where n is the number of points you are taking along each axis. So over here, I have taken 10 to the power 5 points along each axis. So overall, you can imagine how many summation and function evaluations I am having to perform. And that is going to be stored in this variable sum. So it is a parallel program, and it will also involve a reduction. And we have discussed the previous day why reduction is important. Like if you have some accumulator variable which is accumulating something, then in those scenarios, accumulating in parallel, I must say, in those scenarios, reduction is needed. And yeah, so this is how the thing looks. So if you discretize the domain and you take the box at I comma j, so you are going to, so this function is in terms of x and y. So this index has to be transferred to the value of x and y. So that is like we are taking the midpoint of the box. So you go 0.5 more extra and then you multiply it with the step size and then you have the step size square. So this way it gives you the value of the area under that small portion and you add up all those areas to get the whole value of the integral. So you might see that this is a very parallel problem and now we will maybe execute it and see how fast it is compared to direct only CPU execution. So first let's do it with OpenMP. By the way, so as we had discussed in some of the earlier classes, what one of the advantages of OpenACC is that you can use CPU execution. Let's say you don't have a GPU, you can use CPU execution as well. So for that, you can actually use something like TA equals to multi-core. That will give you it will execute this loop in multi-core mode so that you don't need the GPU in that case. So first let's see how this works in multi-core mode. And this is quite a big loop, so it might take a bit of time. So it is taking around 3 seconds. And let's see how much it works in just serial mode. So we will not have any multi-core as well. Okay, so you are saying collapse 2 will improve the execution. I will come to that discussion. Let's do just the serial part. Let's see how long it takes. It will take around 10 to 12 seconds probably. Yeah, 11 seconds. And let's do it using GPU. Okay, now I think you can see what is happening. So again, this might be a very parallel problem, but it does not make sense to do such a simple problem using GPUs. But as an example only, you can see what is happening. Using CPU parallelization, you are getting a time of around 3.3 seconds. Yeah, using serial execution on the CPU, you are getting around 11.9, around 12 seconds. And using GPU acceleration, you can see that you are getting around 2 seconds. So as you see, it is the fastest. And that is because the problem is parallel. Now what I think somebody asked is, what about adding a collapse? Okay, so we will add the collapse and see. Yeah, now you can see that what is happening is it is actually slower than without the collapse. Can anybody guess why? Generally, collapse is supposed to be better. Okay, so this is because what you have to keep in mind is you are also doing a reduction in this problem. So what will happen is, if you are doing a reduction, there is a element of synchronization involved. So what will happen is, if you are doing collapse, what it does is it combines these two loops into a single loop internally. So what will happen is that way, if you are doing a collapse, there it will involve many synchronizations within a particular group of threads. There will be a requirement for synchronization. So in that case, actually avoiding collapse is seen to give a better performance. At least this observation will vary. How it will vary is it will depend upon the system size you are taking. So in certain cases, it might actually be beneficial to use the collapse. So it is a trade-off. Like in this case, we are only parallelizing the outer loop, correct? So in that case, this loop and the sum is getting reduced across that. So there is no that sort of a synchronization occurring for this iteration, this loop. So it actually you have to play around. In certain problems, you have to notice like what value of, if you actually do collapse, it is working better, or if you are not doing collapse, it is working better. It will depend upon how much time it is taking for synchronization. It will depend upon how many iterations you have, things like that. So in at least in this problem size, collapsing will not give you better result. It will actually make your code slower. But in certain cases, it might actually help. So you have to tune the problem according to whatever you have on your hand. So yeah, I think that is okay. I think there is another clause which you can try out. So I will tell this as a general advice. So when I am doing my own coding for my own problems, you just first start with ACC parallel loop. And if you have a reduction, you do reduction. Then you slowly add some clauses, remove clauses, and check whether you are getting good performance. Like vector length, so there is the internal details of a GPU architecture. There is something called a vector. So they have a thread, a vector lane, workers, gangs, and so on and so forth. You can play around with those numbers. In your first try, you don't have to implement all of this, but slowly as you gain experience, you can slowly play around with these values and check if it gives you better performance. So maybe I will just try it with vector length 1024, and I actually see that the performance is more or less same, but slightly worse maybe. This could again be due to some small variations. So you can play around with vector length 512 and check again. So the whole philosophy of doing OpenACC is it is very easy to parallelize, and once you have parallelized it, you can play around incrementally and check various ways of even more optimizing it even more. So this is the way you can do numerical integration. And I mean, you can, if you have some integration which you cannot do by Monte Carlo, or you have some other problem, maybe you can try this out in some example in your problem. Does anyone have any questions regarding this? By the way, let me just check the. Okay, it is fine. Yeah. Okay. Again, if you should again one more thing I have to show you. Like if you see here, it is generating ACC routine sequential. So this is one thing which you have not discussed before. Let's say in all the previous examples we have done in, I think, SAXP and things like that, we had done only fundamental mathematical operations from within a parallel loop. We have done addition, subtraction, and things like that. But if you are going to define a function inside one of these parallel loops, okay, so in that case, you have to write the function separately. For example, I have used a function f here, which is my integrand. You have to write the function f somewhere to tell the compiler that this function is going to be executed on the GPU. The compiler has to create a version for this function to execute on the GPU. To tell the compiler to do that, you have to include another pragma. That pragma is hash pragma ACC routine. Now, up to here, it will be same for all. Now here, inside this function, there is no more parallelization to be obtained. Like you can have certain functions which will have even more loops inside this function, correct? And those loops can be parallelizable. In those situations, you have to say that it is parallelizable, and you have to say either it is vector parallelizable, those you can check up later, but you have to actually tell the compiler what sort of function, and that you are actually defining a function which needs to be executed on the GPU. So maybe we can check if I don't give this hash pragma, what will happen. Yeah, so you see it is actually generating an implicit ACC routine, sequential. So the compiler knows that this function is not available and it will implicitly generate it. And if I give it, it is fine. It will anyway do it. ACC, so if you can see, it is generating ACC routine sequential, and it is generating NVIDIA GPU code for it. So you have to remember that if you are using user-defined functions inside the loop or something, inside some parallel region, you have to define the function with hash pragma ACC routine. PG compiled multi-core codes better than OpenMP compiled in terms of speed. Okay, let's maybe check that out. You have asked a good question. So that doing that is very easy. We'll just go to OMP parallel for, and then we will just compile using -f OpenMP. Let's check integration. Let's time it. It is taking around 3 seconds. How much did it take the last time? I don't remember, but I think it is more or less around the same. I think internally they will do the same thing. So there are not many ways you can parallelize. So if you are going to do OpenMP, OpenMP itself is not it is just an API. It will be reduced down to some machine level execution thing, right? So it will actually depend upon your compiler. So I think this one, if we compile it with GCC, you might see a slight difference in output. Let's just compile this with GCC once. And then time it. I think GCC one is a bit slower. It is quite a bit slower, it seems. So it will actually depend upon, I think I have to put a bit of optimization flags. I had used O3 there. Let's see. Yeah, it is taking around 7 seconds. So as you see, it will actually depend upon how good your compiler is. So you have to play around with OpenMP if you want to do OpenACC TA multicore, or you have to see if your G++ compiler is doing better or your GCC compiler is doing better. I mean, you can also try out other compilation flags. So OGC G++ has a OFast compiler, a compilation flag, which might give it a bit of speed. You see, again, if you use that flag, it will reduce the speed to around 2.66 seconds. So yeah. Okay, I'll just put this back, ACC parallel loop. Maybe let's try out just vector here. Vector length 1024. Oh god, now this is taking time. So yeah, the issue is you have to play around and see what is actually working. I think this vector optimization applied here is not the correct idea. See over here, the compiler itself was generating gang. I had put vector. So that is probably causing the slowdown there. Yeah. So you have to be careful like what you are using, and compiler most of the time does a good enough job. Okay, so this is all about performing the integration. Maybe you can try this code out in your machine. This is pretty simple, and check whether it is working. Okay, so this is all about numerical integration. I will probably upload this codes in some folder and share it with you guys on Google Drive. Next, what we can try out is a matrix vector operation. So what is the type of the operation being tried out? This is called a GEMV. Maybe I'll show it to you what it means. Sorry, I don't have slides today. I was creating these codes, so I have not made slides for this. Maybe I'll make some slides as well and upload it later. Yeah, so GEMV is you are going to do a matrix vector multiplication. So how does it look like? It will be AX plus Y or alpha AX plus Y, where your A is a matrix, X is a vector, Y is a vector. There is maybe a better blast. These are called blast2 functions, GMV. Okay, let's see here. Yeah, you see, so this is like alpha A into X plus beta Y. So this is called a GMV operation, and this might be, this is similar to what you have done for SAXP. So that was just AX plus Y, this where A was a scalar, X was a vector. Here A is a matrix, X is a vector. So you are over there, it was a level 1 blast where you are multiplying a scalar with a vector. Now you have gone to the next step, you are multiplying a matrix with a vector. So let's look at how this looks in the code. Okay, so yeah, so if you look here, I have declared the matrix, and yeah, so this is another important point I will come to in this example, that I have also declared a flat matrix. What do I mean by a flat matrix? In all these BLAS options, routines, you will see that if you have used such a routine, they will ask for a flat matrix. So by a flat matrix, I mean it will not stored, at least in your computer's memory, in contiguous memory positions. Like generally a matrix will be stored such that all the elements are side by side in memory, in contiguous memory locations. And then I have declared X and Y are the two vectors, and I have the three results. Why I have three results? I am executing it in three different modes. First, I am executing it in a CPU mode, where I have just ACC. Okay, I'll put, yeah, by this one here will be MP parallel. We have a CPU mode. We will have a GPU GMV, where we are just executing using a normal matrix, which is not flattened. And then we will have a GPU where the matrix is flattened. It is important to be able to flatten the matrix, since it will give better performance. So if you have an n by n matrix, if you flatten it, you will end up with n square elements. So you are going to define a matrix with n square elements like this. And I have initialized it to some random number, and we have performed the GMV operation. And we have to copy, of course, since we are creating these objects, these arrays on the CPU, we have to copy all this to the GPU, so that we have done using the enter data copy in directive which I had discussed the last date. Yeah. So now let's see what are the results, and I will come to each of them. Yeah, GM. Yeah, GMB. Okay, what is saying? It is pragma for, maybe there is a issue in this one. Correct. Now let's execute it. Okay. Now I'll just go through the output first. So this is your initial. So I have to initialize my array, right? So that is the initialization I have printed. Maybe that is not needed, and this is the. I'll maybe suppress that thing before part. Yeah. So I will now compile it once again. Yeah. So first let us look at the output. So this is after the operations are done. So I have once done it using CPU, once using GPU, and once while it is flattened. So CPU time you see is 0.000471. This is because the number is very small, because I am using a small system size. But you see the CPU time is around, it is something 471 seconds, where with 10 to the power minus 1, 2, 3, 4, 5 around. The GPU time, which is not flattened, is another order of magnitude smaller than this. It is some 471, this is some 59. And if you have flattened the matrix, you see it takes even lesser time than that. And if you look at the output, these are the three vectors which I have just written it. I have printed them: y result 1, y result 2, and y result 3. I have printed them by copying out from the GPU and printing them on the CPU, so that I have to show you that the results are same. Of course, you should always parallelize such that your results are correct. You cannot do a wrong parallelization. So the output, the results are same. So yeah, if the results are same, that means my algorithm is working correctly. Now we have to just scale up the system size and see what is the effect of higher system sizes. Maybe we can use 1500 size vectors. Let's see how much time it takes. Yeah, so you see it takes around half the time. The GPU takes around half the time, and if you have flattened it, it takes an order of magnitude lesser amount of time. So again, if you now look at the code, it is just simple matrix vector multiplication. You have one I loop which goes over all the elements of the vector. For each element, I am taking from y and storing it in y result. And for each element, what I am doing is I am running a smaller loop in between, and I am having a addition of multiplication of this matrix, or as seen here, this matrix with this one. So yeah, this is the operation is pretty straightforward, and since it was alpha ax plus y, so I have to add y again over here. But overall the operation is very easy, but you can see that there is a nice effect of changing your matrix from a normal two-dimensional object to a one-dimensional object. So in that case, you have to be able to index the elements. Like for a normal two-dimensional array, matrix, what do? You write Aij. But if you are going to flatten it out, this Aij will correspond to ai into n plus j, where n is the size of one of the direction of the axis of the matrix. So to convert from a 2D object to a 1D object, you have to follow this indexing difference. If you do that, everything else is just the same. As you can see, I have done a flat is ain into j, ai into n plus j into xj. So yeah, this will give you good performance if you flatten it out. So if any one of you have done CUDA, in CUDA you will see all the BLAS algebra routines you call, they are always using flattened arrays or matrices. So that is one of the reasons why they are using it, so that the memory access becomes easier, and therefore you will have better performance. So this is like matrix vector multiplication. You can do matrix multiplication also. Matrix multiplication is one of the cornerstone things in linear this computational linear algebra thing. Like, it is very important. So you can do matrix multiplication fast. So I have implemented here the most simplest and the most naive algorithm. So when you are actually writing your own codes, it is actually advised not to write your matrix multiplication like this. So what will happen is you should actually always call matrix multiplication libraries which are already available, like cuBLAS and MKL and OpenBLAS and things like that. But for a introduction to parallelization and to learn how it is being done, this is a good enough example. Again, everybody knows what matrix multiplication looks like. It will be A, I, K, B, K, J, and you will sum over all elements K. And for this operation will give you one of the elements I, J. So you can perform this operation in parallel for all I, j, and then you can again, we will see the effect of flattening out the matrix and see how much faster or slower it is working. I hope matrix multiplication algorithm itself is very easy to understand. So that is not the issue. And yeah, over here I have for checking if my algorithm is correct, I have to just print the output of the matrix to see that all the elements, while it is done in either way, it is working. So let's see, it will be GEMM. Yeah. So we will run GEMM. Oh my god, okay. This is printing too many things. Let me just reduce the size right now first. Let's do it with 20 cross 20 matrix first. This is also too large. Let's do with a 10 cross 10 matrix. Yeah, you see, I have printed the result from doing it in both ways. So in that case, the things are matching, all the entries are matching, if you see. So that means my algorithm is now correct. So now we will comment this out and try it for a larger system size. Okay, so this I think you should follow in your own coding as well. Like, you should verify with a small system size where you can verify the result, that if your GPU parallelization is giving the correct answer, you should always verify that, and then you can run it for a larger system size. So this will be a good programming practice. So okay, let's first do with TA equals to multicore and see. Yeah. Now we will run GMM. So it is taking for 1000 around 0.15 seconds normally and 0.102 seconds on CPU if you run for 1000, if you have flattened it. So you see, flattening of the matrix is actually better on CPU as well, because the same principle carries over, that memory is easier to access if it is posted, if it is contained in contiguous locations. So we'll just do it for a larger system size. It should take around 10 seconds maybe. Oh, it is taking a long time. Maybe then we should use a bit smaller. Let's say how long this 5000 cross 5000 matrix takes. A long time. Let's check it on the GPU then. Yeah, you see, GPU is way faster. In CPU mode, I was not able to get a result in some decent time, and in GPU, it is working in half a second. And in flat, okay, in again over here flat, it is actually taking more time. Maybe that is due to something else. I'll have to see. PC. Let's do it for a larger system size, maybe. Hmm. So for the normal, it is taking around 20.2 seconds. By the way, yeah, I am computing the time using the OMP get W time function. So that way, you can internally get the time. This is a function in the omp.h library. So here you see that more or less it is taking the same time. I think my estimate is if you take larger matrices, this will actually become better. That is because there are some internal, like the difference between this and this is, so for every iteration loop, it has to calculate the I into n. This can be actually pre-computed so that on every loop, it does not have to waste cycles computing I into n. All these index computations have not to be computed. So maybe we can try that out and see if that works. So this is like pre-computing the index so that over here, it is not required that many times to compute it. Maybe then we can compute it for in plus j. So, okay, let's try with this one first. Collapse does not match the number of loops. Okay, so if we do this, then it is again a problem because again then collapse will not work. So I think we have to do it here. int in is I into n plus j. So we will do up the whole j part also. Let's see if this improves the performance because I expect that computing those indexes also take a lot of time. So again, it is taking, the normal is taking around 20.2 seconds. Let's see how much time this one takes. Oh, then it is not. So yeah, anyway, so I think you can play around with this and see whatever is actually causing this, in this case, the flat to not work. I feel in this case of matrix multiplication, this is not this, at least this way. While the way I am showing it to you, this naive way of writing 3 loops is not the good way to do it at all. Because again, there are even better ways of doing matrix multiplication. Maybe I can show you one example from the internet. Matrix multiplication. Efficient parallelization. So, efficient algorithm. So there are actually a lot of research going on in which you actually find out even better and better ways of doing matrix multiplication. So, I mean, that is why it is better to use some pre-existing library like cuBLAS and not do it like that. So these things, like whatever algorithm I have shown here, this is the most naive way, but again, this will be a good example. So you can see that it will actually work for parallelization, because you saw that it is actually far better than what is happening on the CPU at least. So that way it is at least some way better than what the other implementation was. Yeah, so maybe people can read this, these sort of papers are there. So this is the naive algorithm we are talking about. This is what I have implemented. But there are many other algorithms, Strassen's algorithm and Vinograd's algorithm and things like that, which are even advanced algorithms which will do matrix multiplication faster. So you might ask, why is such a research thrust behind matrix multiplication? That is because most of your machine learning and all those things, they involve a lot of matrix multiplications, like propagating neural networks and things like that. They will involve a lot of these BLAS operations, matrix vector, matrix operations. So people have written those in a very optimized way, so that you can, so that the calculation is very fast. Yeah. So this goes the case of matrix multiplication. And finally, one of the other things is called which is interesting, is solving linear equations. So for that, again, there are many algorithms available, and most of them are parallelizable. And over here, I will show the implementation of one of them. It is called successive over relaxation, and maybe I'll show the code for that before I'll show it a bit here. It is called successive over relaxation. Yeah. So let's say you have to solve a system of the type Ax equals to b, where A is something, x is this, and b is your coefficient on the right hand side. Sorry, is your constants, and the A is the coefficient. So you can actually decompose this A into 3 parts: the diagonal part, the lower triangular part, and the upper triangular part. And then you can write it out like this, and you can actually create an iterative technique. All these iterative techniques are generally parallelizable. So this equation then can be written as this iteration. So if you remember the first day, the previous day, we were looking at something like SAXP, which was parallelizable. Similarly, that again we had looked at something iteration of SAXP. So for this one is also like an iteration, where you have to take an initial guess. So xi is the ith element of x for step k. You have to take that, and you have to find that, and to find that you need xi at k, xj at k, and again xj at k plus 1. This would look like it is not parallelizable because it involves the k plus 1, but then if you look at it here, j less than I, this is again parallelizable in that part for j less than I. So in that way, you can parallelize the evaluation of the right hand side. And these are summations. Summations can be parallelized, and you have to do this for all values of I. So you have to do for x1, x2. Let's say you have a 5-dimensional system, so you have to do for x1, x2, x3, x4, x5. In large problems, you might have some 100-dimensional equation, things like that. So for those scenarios, you have to do for 100 such things, and for each thing, for each of these things, you can have to perform an addition like this. So these are again very parallel problems. So I have written down an implementation of that, and maybe I can just show you how much speed up is there. I have taken a system size of 20,000, and over here in this method there is a omega, which is a relaxation factor that has to be chosen to get the roots properly. So maybe I will first run it with just MP. No, I'll run it with TA equals to multi-core. I'll time it. It is taking around 2.35 seconds for 20,000 system size on a parallel using CPU. If I run it without multi-core, it will probably take a much longer time, probably. Yeah. So it will, I don't know, it might not finish quickly. So yeah, it is taking around 12 seconds. So now let's run it on the GPU. Okay, it is taking around 6 seconds. Maybe then I'll have to see why CPU parallelization in this case is faster. That one reason could be that these loops we are having to do a lot of reductions. Maybe we can get rid of this loop and maybe check that. Yeah, see, this is what happens. Like, since there is a question of synchronization here, like you have to do a reduction and things like that, doing that inside a parallel loop is actually costly in certain cases. So it is actually better if you do it without a ACC loop reduction here. This will actually be faster. So yeah, and this I have actually implemented that algorithm. So this algorithm is pretty easy to implement. You have to have a new solution, and you will be starting with some initial condition. I have given the initial condition to be 0.1 for all of them, and then you have a tolerance. To do numerical solutions, you have to have a tolerance, and you will also have to have a limit on the number of iterations, so that at least if your tolerance is not matched, if you cross the number of iterations, you should stop your while loop. And then it is pretty straightforward. You calculate the first sum, which is multiplying with sol new. Why have I used sol new here? If you remember that in the first summation in that expression was involving k plus 1, and the sum 2, which is going from I plus 1, that will be only till sol, it will use the older solution. And then you match, you finalize the expression, and you do this for all the values of I. And therefore, your new solution is now ready. Then you have to calculate the error. Error is just maxima of all the individual errors, and you have to copy the new solution back to the old solution, so that this iteration loop, now new solution is the old solution. So you can use it like that. And you see that actually doing the reduction, if you see what I had just shown, that successive over relaxation, in this case, doing these summations in parallel is actually leading to a bit of slowdown. So yeah, you have to be able to like identify which things can be parallelized and actually play around with them. Play around, put a reduction, put a parallel loop, see if you are getting a speed up, see if you are not getting a speed up and things like that. So in this way, this method can be used to solve a set of linear equations using this method of successive over relaxation. Okay, so I will come back to this. It is past 3 o'clock. Anybody has any questions then maybe regarding to this thing? I will probably share all these codes with you. You can try it out or you can write them yourselves as well. These are very simple to write. This successive relaxation and all this, but the thing is you should only write this for learning. All these things, equation solving, matrix multiplication, everything is actually available in some BLAS library. Maybe I will show that so that you know what to look for. So there is something called cuBLAS. Maybe cuBLAS can come later. You can probably look at OpenBLAS if you're just doing for a CPU programming. These are not only available for GPU, but these are also available for CPU as well. So you can actually install OpenBLAS and you directly use the functions because these are very optimized functions, and you can be sure that they are very optimized and they will be faster than whatever you write. It will actually be faster than whatever you are anyway able to write. So for example, here you see they have written that dgem function, that gemm function we were discussing right now. It is actually predefined. Gemm they have done and things like that. So that you don't have to write it yourself. And this implementation will be very complicated. Maybe we can take a look at it later. And those are very efficient. They have optimized for performance, memory access, and things like that. That way, for technicality, this OpenBLAS and cuBLAS is for GPU execution, as I had shown before. It is from NVIDIA. cuBLAS and all is better. See, this is the basic linear algebra on NVIDIA GPUs. I think AMD also has some sort of a library for this, for execution on their GPU. And they have written there the complete support for all 152 BLAS routines, half precision, integer matrix, gem and gem extension, so on and so forth, tuned for various sizes in deep learning, things like that. Yeah, so they also have a multi-GPU matrix multiplication which can be distributed from among multi-devices. You can use that as well. So these are what is available. So these examples are like we generally do for learning purpose, but you should not use them in your own research work where you are writing something which needs to be very fast. Okay, so this is all for today. In the last class, we will look at how you can solve ODEs and PDEs and things like that. So that and that will be like other part of the class the next day. So I hope today it is fine. Anybody has any doubts or any discussion points for today's what we have discussed today? Okay. So if there is no further discussion, maybe I'll just stop the recording here.